Our next presenter is Peter Landon from BTI Systems, who will be talking about why operators need Transport SDN, which is not just another SDN presentation.
Oh, actually, I guess it is another SDN presentation. So yeah, I'd like to take a few minutes to talk about SDN, but I'd like to focus on Transport SDN. I'm sure you've heard a presentation or two on how SDN is going to revolutionize the way network applications are delivered. You've also heard that it's just a rehash of SNMP and GMPLS, but I think it's actually somewhere in between, so I focused on that. The first few releases of OpenFlow really were focused on L2 and above, with little focus on layer 0 or 1. The optical networking, the ONF has been working on the transport extension for OpenFlow, and they're actually going to ratify a protocol document that'll give you the requirements for L0 and L1 SDN. So why do I feel that optical transport SDN is important? See an example here of a router connected to an optical transport box. It has a couple of 10 gig E-links being transported over an O2.4. Without SDN control over the optical transport box, any changes you make to those ports have to be done manually. So if we have a case of adding, let's say, another 100 gig link between the router and the optical transport box, if you've got SDN control over the transport, you can actually change the modulation format through software from a DPSK to a 16 QAM, effectively doubling the transfer rate, the bandwidth, and that's without a truck roll, without an NMS management interface, and no extra resource. So you might ask, why wouldn't you simply configure this port and leave it nailed up to 200 gig in the first place? And the answer to that is actually power. The higher modulation formats are actually quite power hungry. And if you were to do it across your network, you would impact your power budget quite substantially. So having a dynamic approach to the port speed and configuration can actually save power. Another aspect that's valuable is including transport layer in a unified control plane reduces the risk of the dreaded vendor lock-in. Without SDN control over the transport layer, you would need another NMS controlling the NE, which is most likely vendor proprietary. And if you have the same software controlling both the router and the optical network, it frees you to deploy gear of your choice. Another aspect of vendor lock-in, especially in coherent systems, is the FEC that's selected on the optical link. With new coherent systems, many of them use soft decision spec, which is a proprietary, most likely a proprietary algorithm on the box. But a lot of the vendors or the framer ASICs within the transport gear have HDFEC built in, and they can actually provide coding gain that gives you reach extension sufficient for the metro space, and again, under software control. Now, when you pull the domains together, you can actually multiply the value here. SDN allows for the concept of federated domains, which means that it's not actually proposing that the one controller will have control over every single NE in the network. Rather, there's individual domains that are under control, and each of these domains are configured to provide a well-defined set of capabilities to the top-level controller, and they're advertised to that controller and can be configured across obviously a very large network. So here we have a another example of a data center interconnect where some of the clients are TDM, some of them are packet, and some of them are a mix. Now, there are vendors today providing a converged packet optical solution, which, when combined with an SDN converged control infrastructure, it gives you a seamless way to transition between traditional TDM services like Sonnet SDH into Ethernet-based service. Because the control plane is already aware of these ports, it makes this transition more seamless. It's another factor that's driving the value of Transport SDN, because without these elements, having an open standard control plane just isn't valuable. And as a side note, having the programmable modulation format on the line side can reduce your CapEx as well, because you can use the same pack and just reconfigure it as fiber aging or for different channel qualities. So now I'd like to get into a couple of use cases. The first one is actually a revenue opportunity for a network as a service. By having the control of the underlying optical transport network, operators can slice their networks dynamically, including the optical layer, and provide customers with a way of achieving a goal or an application rather than just presenting them with a simple view of their network. It goes from a concept of having to connect port X to port Y to, I want this functionality, and they get what they want, not have to worry about how they have to do it and all the details. And the second use case is a little bit different. We're talking about now is the dynamic adjustment of adjacencies. And in other words, this is being able to change the bandwidth between ports dynamically on the fly. And this is different than bandwidth on demand, which getting a lot of attention these days, and for good reason. The difference is that this change of the bandwidth happens through programming of the controller, and it's reacting to the nature of the incoming data. Chart in the corner, it's a bit of an eye chart, but all it's saying is how the peak traffic in North America is dominated by streaming or real-time entertainment. And these peak traffic flows are described sometimes as elephant flows, and there are a few different types of elephant flows. A streaming movie, for example, would be a medium-term elephant flow. Doing a data backup between two NASA sites of hundreds of gigabits would be considered a long-term flow. These elephant flows, though, can consume bandwidth to the point of trampling mouse flows, which have proprietary or data that's high priority, and so SDN can help with this as well. In this use case, we have to make a few assumptions. One is that there's an overcapacity in your network, either through shared restoration resources or production advance. And the other is that it's a mesh network, ROADM or other ways, with multiple connections endpoints. So in this case, you have, let's say, a VM migration or a data backup between data center A on the left and data center B. Without SDN control, the traffic shaping will start, and there exists a possibility that your mouse flows will get trampled on the same path. With an SDN implementation, flow marking will indicate the elephant flow to the controller, and that will trigger the controller to diversely route the data over what might be a protection link or just some overcapacity between the two nodes. Now, because the controller is aware of the L0 architecture and the network topology, it can do this rerouting automatically. Once the elephant flow is complete, that connection can be taken down and the bandwidth then available to other applications. And so I dedicated a slide to vendor lock-in because I think personally that this is one of the biggest driving factors for SDN and Transport SDN in particular. The goal is to get to a common control plane between L0, L1, and above, but also between vendors. This is going to reduce the number of NMS that the operators have to learn and manage, but it also will provide a framework for the operator to deploy equipment of choice as the needs change and as new technologies are introduced. So how does Transport SDN work? Obviously, there's a fundamental difference between L2 and optical and pure optical and OTN. With packet, you've got a header. You can examine it, match it, do wildcard compares against it. But for a circuit switch signal, you need to do something different. So for OTN and electrical-based signals, it's done through signal type, an ODU1, an ODU2, what have you, or if it's a tributary, it's location and time. And for wavelengths, we use its frequency or the channel within the grid. In the case of adjacency discovery for L2, which might be LLDP or OSPF, transport uses out-of-band channels or in-band channels rather, like GCC, DCC, or between ROTAM, an optical supervisory channel. Now that's not the control plane. That's something different. This is actually just to communicate between nodes. So at this point, you might be asking yourself, this all sounds great, but real networks are much more complex, and there's a lot of details here that we're just glossing over. And that's right. Two good examples that the ONF is dealing with right now is how to handle OAM and protection switching. Just these types of functions are repetitive, they're complex, they require communication between the NE and the controller, and that kind of goes against the concept of SDN and having that separation. So they've introduced a concept of autonomous function, and autonomous function will implement a function inside the hardware and be abstracted towards the controller. Just to get into a bit of details. So what is an autonomous function? It's an autonomous function is a monolithic entity. In other words, it follows a defined implementation that's already been set out in a standards body, and it does not deviate from it. So if we talk about OAM autonomous functions specifically, the intent isn't to reinvent how we do it. It's to do what is already deployed. And for the functions in the hardware, you can configure it using netconf or ofmega or what have you, and that portion of the autonomous function will be abstracted to the controller. Different layers have different tools and needs, so the autonomous function needs to be usable across different layers, and there also has to be a wide range of support for current functions and functions that will exist in the future. And again, it's important to point out that the autonomous function doesn't go into or define an implementation. It is totally abstract. So as a closer look at the autonomous function, as I mentioned, it's the function itself is pre-configured with whatever needs necessary netconf or ofmega, and then it's associated with the externally configured object and addressed by a reference within the match action table. And it's, again, important to note that the processes internal to the autonomous function are not accessible, or then there's no parameters that are set. So one of the questions I got asked when I submitted this was, Transport SDN just GMPLS, same thing. And on paper, there are a lot of similarities that you can point to, especially if you consider the peer model for GMPLS, the single instance, the protocol across packet and circuit. The peer model, though, hasn't really taken off because of practicalities of organizational boundaries and the limits on information sharing. So it's increased the load on underlying protocols that distribute link information, both packet and optical or transport layer. So what has found favor and is actually being used within the ONF instructively is the overlay model, which was formalized by the ITU as ASON, or automatically switched optical network. But this methodology still separates the IP layer and the transport layer, with requests for services made across unis within the network. And it propagates, again, vendor islands and proprietary vendor control across the transport layer, and doesn't give you a way to request transport service dynamically. So by abstracting the underlying forwarding plane and using distributed system techniques, we can eliminate the vendor island, and the control plane complexity is reduced substantially, which will aid in actually having it adopted across network. I'm going to give a couple of concrete examples on what some operators are doing now and what how SDN is helping. Now, I found it surprising to learn that a couple of tier 1 vendors actually use spreadsheets to track connectivity between their routers and their transport gear. And there's a couple of really good reasons why. Transport, again, unique in that there's no headers to examine. So what you might do with LLDP at the packet layer, you can't do a transport layer. And the way transport gear is used in a lot of data center interconnect is the transparent pipe using G sub 43 or some method to encapsulate packets. So without a method to do it automatically, you're forced to use spreadsheets. So with SDN control, or the knowledge that the controller will have on the transport layer, the controller is aware of the port, and it can dynamically track what's connected. And it can be another resource for debugging misconnection and also help with task planning as well. So I couldn't do this presentation without talking a little bit about bandwidth on demand. I think it's the #1 application that people talk about with SDN. With good reason. I think it's a valuable application with a lot of real-world uses. And so in this example, a little bit hard to see, but what we have is a couple of customers on the lower left and right, and some content service provider CSPs on the top left and right. So it's a typical network diagram, but the difference here is that the connectivity links between customer and a given CSP are not continuous, nailed up links. They are configured on demand. And from a customer perspective, they only see the network assets that they need and that they use. And they can, again, use the application or portal to configure what they need without having to figure out how they go about it. It's transparent to them. And from a service provider, the bandwidth allocation is conserved because there's no need to nail up the connection when it's not being used. It provides a means of a form of stat muxing, which will in turn reduce CapEx. And then the assets can be assigned to individual customers, which aids in efficiency when you're doing your capacity planning. So in summary, I believe there are a number of benefits to transport SDN. From an OpEx perspective, it reduces or eliminates the separate packet and optical teams, or at least combines them. From a CapEx perspective, homogenizing the physical network, you can reuse PEC codes and configure them through software. You can access new revenue streams with network as a service, for example, and overall simplification of the overall picture of the network down to the L0 and optical path is beneficial.
Thank you very much. Are there any questions from the room? Thank you.